The transshipment problem embeds a whole variety of other problems. And these problems inherit the properties of the transshipment problem, in particular, the integrality of the optimal solution if the data is integer. In this video, we introduce the shortest path problem and show that it is actually an instance of the transshipment problem. Each of you has probably used an online tool to calculate shortest path. The problem can be defined as follows. We consider a network with nodes and arcs. In this example, the nodes are intersections and the arcs represent roads in the city. Each arc is associated with a cost. In this example, this can be the length or maybe the travel time along the arc. And then we consider an origin and a destination. In this case, the origin is the EPFL campus and the destination is the Lausanne train station. The problem consists in finding a simple forward path from the origin to the destination with the smallest possible cost. The path must be simple so that we don't use the same nodes twice, and must be forward, meaning that we cannot go against the direction of the arc. There are various versions of this problem. The one that I've just described is called the single origin, single destination problem. But we can also write the problem as a single origin, all destinations. In this case, we would like for each possible destination to calculate the shortest path from the origin to this destination. Symmetrically, we have a version of the problem which is from all origins to a single destination. And finally, we have a version from all origins to all destinations. In this video, we will focus on the single origin, single destination problem. And later on, we will see the single origin, all destination problem. In a transshipment problem, the cost of a path is the sum of the cost of each arc. If the arc is a forward arc, the cost is added. If the arc is a backward arc, the cost is subtracted. But in this case, because we are looking for forward path only, we have that the cost of a path is equal to the sum over all arc in the path of Cij xij. This is a simplification because we are looking for forward path. In order to model the shortest path problem as a transshipment problem, what we will do is to send one unit of flow from the origin to the destination. And the transshipment problem will identify the routing of this flow through the network to minimize all the costs. In that case, we need to define the data of the problem, that is the supply, demand information, and the capacities on the arc. The supply at node O, at the origin, will be 1 because this is where we are injecting this unit of flow. SO equals 1. If we look at the destination now, the supply at D will be -1 because this is where the unit of flow reaches the destination and gets out of the network. And at each other node, that is not the origin and not the destination, these are just transshipment nodes, so S of I must be equal to 0. Then we need to impose the capacities. We need Xij to be non-negative because we don't want the path to use backward arcs. And we need also the flow not to exceed 1, not because the optimal solution is integer. We know that it will be only 0 or 1. And this will be characterizing the shortest path. And actually the cost of the path can be simplified. We calculated the cost of the path to be equal to the sum of over all the arcs of the path of Cij xij. But now we know that in the optimal solution, this xij will actually be either 0 or 1, which means that we can actually calculate the cost of the path as simply the sum of the cost of the arcs. So if we summarize, the data of the transshipment problem are the following. The cost on each arc is Cij. The supply at the origin is SO equal 1. The supply at the destination is d equals -1. The supply at any other node is 0. The lower bound on each arc is 0. And the upper bound on each arc is 1. We can therefore write the shortest path problem as the minimization over x in Rn of the sum over all the arcs in the network of Cij xij, subject to the first constraint is the flow conservation constraint for origin O, which says that the divergence of node O is equal to 1. Similarly, the second constraint is the flow conservation constraint for destination D, which says that the divergence at D must be equal to -1. And for each other node I, which is not the origin or not the destination, we have a flow conservation constraint that says that the divergence at I must be equal to 0. And finally, we have the capacity constraints, which says that xij must be between 0 and 1 for all arc in the network. This is the formulation of the shortest path problem as a transshipment problem. The shortest path problem is a transshipment problem where we send one unit of flow from the origin to the destination. And in that case, the cost of the path is simply the sum of the cost of all arcs in the path.